Telescope and the fact that we finished all of the major deployments today. I am Karen Fox with NASA's Office of Communications, and we are coming to you from the Space Telescope Science Institute in Baltimore, Maryland, which houses the Mission Operations Center, which you can see behind us. We have one microphone today, we have one camera. We are doing this right after the deployments, so bear with us as one person gets up at a time. We are following both CDC and the Institute's COVID rules today. So everyone in the room has been vaccinated, everyone has tested negative recently, and everyone will be wearing a mask for the entire time. We have two panels for you. Each one will last about half an hour. The first is focused on what has been happening for the last 14 days leading up until now. And the second will be focused on what is coming up going forward. We will be taking questions from the media. That will be the focus. We'll just have a few remarks at the beginning. And for that, you press *1 to get into the queue. And let me list our speakers for the first section. We have Bill Oakes, the Webb Project Manager at NASA Goddard. We have Mike Menzel, the Mission Systems Engineer at Goddard. Scott Willoughby, Vice President and Program Manager for Webb at Northrop Grumman. Vince Heeg, Deputy Program Manager for Webb at Northrop Grumman, and Nancy Schauger, Deployment Operations with Northrop Grumman. Now, her voice will be one that you would have heard today if you listened to our broadcast on the operations loop, talking through what was happening, so you can always ask her a little bit about how that went. And with that, I will toss it to Bill for starters.
Thank you, Karen. So, today's been a really remarkable day. We still have about 5.5 months of commissioning left, but these last 2 weeks have truly been amazing. Today represents the beginning of a journey for this incredible machine to its discoveries that it will be making in the future. JWST itself is an amazing mission, and thousands of people have worked on it, and I can never thank them all enough, every individual one, for the contributions that they have made to getting us to today. This journey has been really remarkable. The successes over the last 2 weeks is truly a tribute to the people of the JWST program. Their diligence and passion for JWST is second to none. And personally, if you heard my comments on the voice loops earlier, I am truly, and I have to repeat them here, I am honored and humbled every day to be working with this team. And with that, I'll turn it over to the next speaker.
It will be questions, and we can have our operator step in and give information how to get on the queue and tell us who the first question is from. Thanks.
Certainly. If you would like to ask a question, please press *1. Our first question today is from Bill Harwood from CBS News. Bill Harwood, your line is open.
Hey, thank you. Sorry about that. For Bill Ox, you told us before launch you were 100% confident all the deploys would work exactly as planned, and I remember thinking at the time you might be jinxing it, but that clearly wasn't the case. So how big of an engineering challenge was all this? Was it as easy as it looked, or was it really as difficult as we had all been led to believe, because it sure seemed to go smoothly? Thanks.
It's not as easy as it looks, but the easiness that you saw, again, like I mentioned earlier, is just a tribute to the folks. We went through what I feel now is the exact right amount of testing, the exact right amount of engineering audits, the exact right amount of tweaks to the design as we've gone through this journey of manufacturing and then launching this telescope. The fact that it looked easy just emphasizes that we did all the right things leading up to this moment.
Our next question is from Elizabeth Howell from space.com.
This one is also for Bill. Can you give a sense of how the teams are feeling, how the teams are doing? I know that it's been a very busy couple of weeks since the launch, and over obviously usually a very busy time for folks anyway. So how's everyone doing?
Everyone is doing excellent. I think everyone is extraordinarily excited at this point. I don't think there was one point during the entire last 2 weeks, and even the period leading up to launch, down at the launch site, where anybody felt down, slowed down. I mean, we're all a little tired, but besides that, we are on an incredible high right now.
Thank you. Our next question is from Jeff Faust, Space News.
Yeah, good afternoon, and congratulations on the successful deployment. I just wanted to confirm, we heard a lot about, leading up to the launch, about these 344 single-point failures. At this point, have all of those been retired, and if not, what might be left that would be associated with other aspects of the spacecraft? Thank you.
Hi, my name is Mike Menzel. I'm the mission systems engineer, and there are 49 single-point failures out of the original 344 that are not retired and will not be retired for the duration of the mission. These 49 are typical of all missions, things like propulsion tanks, things like that. And of those 49, 15 are associated with the instruments, which means if any one of them went, such as a filter wheel failing, we would not fail the mission. We would just fail one of the science objectives associated with that.
Thank you. Our next question is from Robert Perlman, Collect Space.
Hi, congratulations on the deployment. I think for Mike, given that there were no cameras to send back images, is there anything for which you didn't have telemetry to now say that the telescope looks exactly like the artist renderings or the computer animations or even the engineering tests we saw here on Earth?
Can you repeat that question, please?
Not telemetry in terms of the configuration.
Well, there are a couple of minor things that aren't telemetered, but whereas if we don't have what we call primary telemetry, we have secondary telemetry. And that secondary telemetry gives us verification that what we think is going on really is going on. So in reality, given the secondary and primary telemetry points that we have, the configuration of the observatory that we're demonstrating or that we're illustrating is pretty accurate right now. So I would say that, you know, whereas we might be missing certain primary telemetry on some certain items, the secondary telemetry that we have really confirms that our configuration is as we're showing it.
Thank you. Our next question is from Marina Corin from The Atlantic.
Hi, everyone. Congratulations. 2 questions for Mike and Scott. Are you almost surprised the deployment sequence went as well as it did? Were you bracing for a more difficult deployment given how risky and complicated you expected this process to be? And the second question, were there any issues that came up during the deployment that you haven't told us about yet? Thanks.
I'm going to let Mike answer the second question. You actually answered the first question in your question, which is we worried about it on the ground. What we focused on was, you know, design, test, verification, and if need be, redesign and retest and re-verification. So our entire objective was wring this out on the ground so that when we went into space and we followed that timeline, we did expect that it would go right. Maybe we'd see something new. We'd see a behavior of, you know, sun angle or how the thermal was or how certain things call it confessed to us. But the reality was everything we did to wring our hands on the ground and have those sleepless nights led to a wonderful last 16 days.
Okay, so is there anything that we didn't tell you? I doubt that seriously. There's always a couple of, you know, minor alarms that go off that's really more like housekeeping than anything else. But other than that, I think you're aware of the incidents or the anomalies that have occurred. And most of them, by the way, were very minor compared to the ones we practiced in our rehearsals.
Thank you. Our next question is from Jim Siegel from NASA Tech.
Thank you for taking my question, and congratulations to the entire team. I noticed in looking at the photos and pictures, the video that was on the screen, that there were a number of people in the Michigan Operations Center, and I assume that there were others and other buildings or other rooms within the building. And I'm interested in roughly how many people were in the mission operations room during that deployment, and how many other people, perhaps around the world, were also involved in the deployment that we saw today.
So we run in the entire Mission Ops Center. So it's not just the one room, but in this section of the building that we consider the Mission Ops Center, we run 95 people per shift for deployment operations. As far as around the world, the other folks that were involved were actually out at Northrop Grumman in the factory, and they provided support, in particular during the Sunshield deployment, where we had our independent verification, essentially engineering model, full-scale engineering model, all set up, and it went through every step of the deployment with us. So if we would have had a problem, we would have been able to go back and look at that. This helped determine what the issue might have been.
Thank you. Our next question is from Marcia Dunn from Associated Press.
Hello. Question for you, Bill. I'm wondering if you think it's all downhill from here. The first 2 weeks were obviously risky, complicated, never before attempted. If it was summiting Mount Everest, landing on Mars, how do you view the rest of the mission, actually? And does the team get a rest, or are you going to be moving immediately into the alignment of the 18-year segment? Thanks.
It's not downhill from here. It's all kind of a level playing field. Obviously, with like Mike talked about, the single point failures associated with deployments, that was probably the highest risk part of the mission. That doesn't mean all our risk goes away, and doesn't mean we lose our intensity as far as maintaining our discipline for the mission. You'll actually get more information about what comes next, but what we do next is we take each of the individual mirror segments and we deploy them off of their launch stowed position.
Thank you. Our next question is from Stephen Clark, Space Flight Now.
Thank you. Congratulations. I wanted to follow up on an earlier question about making it look easy. There's a lot of talk before the mission about this being perhaps the most complicated spacecraft deployment in history in space. You did make it look easy. It was nearly perfect. And just wondering, in retrospect, how would you rank this deployment process up against anything else that's been done in history? And just if you could take like an after action look back on, was it really as complicated as you said it was before the mission? Thanks.
I'll take a part and let Mike go, but there's really two aspects. One is the practice that we did on the ground, but this was our fourth Sunshield deployment. So we did one as we integrated on the vehicle, and then we did one at what's called the observatory level. After the optics were integrated with the bus and the Sunshield, we did one before an environmental test and one after. So this is our fourth shot at it, and we learned in each of those successive, pretty clean one on number 3, which verified that we worked after surviving a simulated rocket ride. But the other thing is you design for worst case. You design sometimes for worst case. So within our design, we always had margin to go to. We had more motor power if we needed to drive it out. We had more strength in something if we needed to pull on it harder or push on it harder. So you build in that, because knowing surviving the first days and the first weeks often is the most stressing environment that a satellite goes through. This is why they tend to last, well beyond their initial, intended mission life. So you don't over-design, but you design for things that you can't always test. So analytically, you make things worst case. On the ground, you push harder, you go colder, you go hotter, and you do all of that stuff on the ground so that you swim right in the middle of the lane after your launch. So it's really a combination of that and practice.
Yeah, and in one of the other press conferences, I pointed out that when it comes to the deployments of this observatory, there are two kind of unique things about the deployments. First, was a sun shield, and that was deploying large, indeterministic, floppity structure with a lot of cables, a lot of tennis court-sized membranes that could float to places you don't want them to float to in zero-G. And through our testing and through our design, we controlled that, and Northrop and the Sunshield team did a great job on that. The second part of our deployments are what I call precision deployments. We're actually rebuilding and retuning an optical and infrared telescope remotely. And those deployments had to happen such that they position the mirrors accurately enough so that our wavefront sensing and control optical engineers can start taking that state where they're in and tune a telescope. So between the fact that we had large indeterministic deployments like the Sunshield, then we had large precision deployments like in the OTE, like in the telescope, this has been arguably the most challenging deployment program ever done by NASA.
Thank you. Our next question is from David Curley from the Discovery Channel.
Thank you very much. Bill, if I could get you to come back up one more time. We've heard this through this process over the last couple of months, that great confidence, but we had sleepless nights. I get that, and I do hear relief in your voice, especially to the answer to the first question. Can you just talk about that, and then the bigger picture of the science when the first image from all the mirrors, once they've been all set, comes back, and what all this work has meant and should mean?
As far as relief goes, yes. I mean, there's obviously a huge feeling of relief. A couple of times people have made comments about the easiness of the deployments. Just because we made it look easy doesn't mean it was easy. But it is, like I mentioned earlier, just a tribute to everyone who's worked on this to get us through it. But yes, there was a huge sigh of relief. I think you could see that if you watched the video of us being in there today when that final mirror got latched and the folks in the back room were doing the wave. We're all up giving each other high fives, so that's all of a sign of relief. As far as the first science goes, there will be a couple of science folks on the next panel. They can discuss that. But obviously, we are all looking forward to that time when they release those first images and first spectrographs and spectrum and really talk about some of the amazing discoveries that we'll be making and demonstrating that we'll be making with JWST.
Let them know how you feel, Nancy. You called out all the insurance.
Go ahead, yes.
So part of, I think, making it look easy was we developed all our procedures very early. We were using them back in panel integration. We used them through INT. We tested as much flight-like as we could from day one. And so by the time we went through rehearsals and got here, everyone who was supporting was very familiar with what all the procedures did, how they work, and what to expect, in terms of data return. So we were lucky to some extent, smart to some extent, but everything, was just very smooth and, very predictable. So it's a relief.
Thank you. Our next question is from Reese Nations from the Well News, Washington, D.C.
Hey, thanks for the call, everyone. It's a pleasure to be hearing your voices today. Congratulations on the successful mission. I just wanted to ask real quickly about the November payload processing incident where a clamp band broke. How close did that come to damaging the vehicle, and how would that complicated the efforts from there going forward? It seems that you guys touched on that earlier a little bit. Everything's going smoothly, but was that cutting it a little close there for your liking?
I think you were talking about the clamp band incident down at the launch site. There was no damage to the spacecraft. We proved that down at the launch site through our testing that we've done. We did some specific testing as well as running an aliveness test. We've done a boatload of analysis to determine that the shock event that we saw did no damage to the spacecraft, and we've demonstrated that today from a standpoint of deployments. So I hope that answers your question.
Thank you. Our next question is from Leo Enright from Irish Television.
Thanks very much for doing this, and congratulations. The administrator a few minutes ago on NASA TV made a passing reference to an L2 insertion burn that he pointed out was of some importance. Could you talk a little bit about that? In particular, I'm looking as I'm talking to you at the cruising speed, which just fell to 395 meters a second. I mean, you're not going much faster than a 747 jet at the moment. And I'm just wondering, I mean, what speed are you going to be doing when you get up the hill to L2? And is there anything that really worries you about that burn, or are you comfortable that you've already had enough burns to put that risk to one side?
Yeah, the burn you're referring to is what we call the MCC2 burn. And to be honest with you, we're not at all worried about it. It's a very minor burn. I don't actually have the Delta V available right now, but it's a very minor burn. It would be done at about launch plus 29 days. And after that burn, we pretty much actually fall into the orbit around the L2 point. So we do have to do the burn, but in terms of its timing and in terms of its Delta V, compared to some of the other burns we've already successfully accomplished and and implemented, this isn't all that critical. So we're not that worried about this burn at all.
Thank you. Our next question is from Marcia Smith, spacepolicyonline.com.
Thanks so much. I'd be interested in hearing from the Northrop Grumman representatives how this all looks from their standpoint. It's been a long haul to get James Webb built, and probably many more years than Northrop Grumman had planned. So I'm curious about how it looks from a corporate perspective and what lessons you may have learned on this program that can be applicable to others. And I'm also curious about the visualization tool that NASA has been showing, and which has been very, very helpful. And I'm curious, is that something Northrop Grumman developed, or where did that come from? And my last question is, what is Northrop Grumman's role going forward? Are you going to be involved in operations from here on, or is your job pretty much done?
Let me address a little and have Vince come up. The one thing that made this special for us is, as Northrop, as an industry player, works with NASA, it's different than most of our customers because NASA designs and builds and tests things. So we're going to their shop at Goddard and we're watching hardware get built and tested on shaker tables or at Johnson as we're building. So when you talk about, I don't call it a lesson learned, but certainly what we learned to do was collaborate at an engineering level. That's how you make something. There's no way any one company could have done the James Webb Space Telescope. So as a company working joint with NASA, as we had back on the Chandra X-ray telescope and the Compton Gamma Ray telescope, we have decades of experience of building things together, which sometimes can create tension, but you hope it's a healthy tension as engineers debate, and that brings out the best of you. And then it's, okay, what we agree to, and Bill and I will often broker that for the teams, and then go focus on it and get it done. So I think that relationship, got perfected over the years. From a lessons learned perspective, I always look at the management perspective of what does it take to manage something this big, this complex? How do you make risk-based decisions? There isn't a meeting we usually walked out of where we just focused on plan A, where we didn't say, where is plan B? Where were we going to be ready if we had to make a different, if the result doesn't come out? We don't want to run a test before knowing what to expect as the results, so we're not reacting after the fact, we're preparing before the fact. And that's where we brought the best out of each other. I'll let Mike or Bill talk about the visualization tool, but in terms of the future, we are part of the operations. We have a test bed. We have an electrical test bed also, in addition to a mechanical test bed that we'll have up and running. If there's software patches, if there's questions on orbit, we'll run those back. You don't want to do something for first time in a vehicle you don't have to do, so we'll demonstrate that. I don't know if add a little, Vince.
Yeah, I would just say, certainly there's a lot of lessons learned from an INT perspective, which is really most of my background. It was incredibly complex. I mean, just for us for the IVA that Bill was talking about back at the factory, it took that team 45 days to fold it back up and stow it so that we could deploy as we watched the deployments here live. And then when you look at, you look at the sun shield and everybody's asking, is it really that complicated? If you look at the guts of that, right, it's feet and feet of cables and pulleys and dog houses and clips, all this stuff that has to work perfect. I mean, are you kidding me? It is complex, but it's a tribute to the technicians and engineers that last touched the satellite at Space Park. They just diligently made sure that everything they did was going to be perfect. And that's why we just had the best deployment of the sun shield that we've had in the 4 times that we've done it. So congratulations to those guys.
Thank you. Our next
The visualization tool is actually part.
I apologize.
Yeah, the visualization tool is actually part of the ground system. It was provided by Raytheon out of Denver. And basically it's made up of our various drawings of the telescope that we've taken and converted into an animation. But the whole thing is driven by telemetry from the spacecraft, such that as the configuration changed on the spacecraft, we could see it change on the ground.
Thank you. Our next question is from Alicia Sowers from Mashable.
Hi, thank you for taking my question. Congratulations. The observatory hasn't reached its destination yet, and all of these deployments have occurred while Webb is traveling to L2. So I'm just kind of wondering, is there any risk that the structures could be damaged or come out of alignment as it continues toward its destination? And the other thing I wanted to ask was, you've got a really large audience right now on the edge of their seats for Webb, and I'm just wondering, there's a long time between now and June when we're going to see those images. I'm wondering if there are any upcoming milestones that people can look forward to in the meantime. Thank you.
First, there are no dangers to the structure by virtue of where we are in the orbit. Where we are in the orbit right now is a very benign trajectory. And as I said before, we're literally, after the MCC2, we'll literally fall into orbit around the L2 point. And then for the other question was, what's coming up? You'll hear that on the. That's a better question for the next panel coming up.
Thank you. Our next question is from Irene Klotz, Aviation Week.
Good afternoon. For Northrop Grumman, probably Mr. Willoughby, does the deployment complete the JWST primary contract and then you switch over to this technical support, or is it all still part of the same contract, or did that initial contract complete when the telescope was turned over to NASA?
So our primary contract goes to launch plus 1 year. We did have, Bill and I, a signing party down at the launch base when we do what's called the DD-250, so that transfer of ownership of the vehicle, because we had as we completed out putting final MLI and parts on the vehicle. So, but with that, that's still under our prime contract. So in terms of that responsibility, certainly commissioning for the next 6 months and 6 months of science missions, and then we'll transition to what's called the Phase E into the O&M part of it.
Thank you. Our next question is from Ken Kramer, Space Up Close.
Hi, thank you for doing this, taking my question, and congratulations on the spectacular success there. My question is about lessons learned. You've accomplished this great deployment. What are the lessons learned going forward, and how would you apply this to larger deployable telescopes? I wonder if you could speculate what is possible beyond Webb now that you have accomplished this. Thank you.
Okay, well, in terms of lessons learned, we're compiling that. A lot of us are compiling that now. I think it's a little too premature for me to comment on that, honestly. Our deployments went so smooth, it would be hard right now to have some obvious lessons learned from that. We'd probably, when I caucus with the engineering teams and we start compiling our lessons learned, it might be some of the telemetries that we found a little funny, maybe some telemetry, extra secondary telemetry procedures that we might want to do, things like that. So right now, the honest answer would be too early for me to give you some real definitive lessons learned from this. But overall, it went smoothly, and you know, I think the lessons learned would be something along the lines of, hey, here's how we should plan contingencies. Here's how we should, you know, provide other telemetry points, things like that.
I'd like to add a little bit. You talk about what's next. We proved that we could build a telescope bigger than the top of the rocket, right? I mean, something that had to be folded, the optics itself, right? The sun shield that had to be stowed. And in that, we learned in a positive way that how you test and how you test like you fly, which is always a #1 mantra on what you do right on the ground, we had to come up with alternate ways. So when we had a sun shield too big for the chamber, we took that, we scaled it to 1/3, every feature perfect to a 1/3 scale, put it in a chamber, took our computer model, scaled that to a 1/3. Test correlated the model, so we did have a cornering in terms of a test verified, and then dimensionally controlled it as we scaled it out, right? So the team found solutions where we were to some degree limited by the physics, right, and the ability for chambers on there, and that's what I'd call a hugely positive lesson learned, because I don't think our appetite's going to get smaller from Webb, right? So when you look at that, we're going to have similar limitations, and we have now evidence, and we're going to be building more, certainly over the next 5.5 months, of how our ability to correlate models and subscale articles and then scale it up and predict it. And right now, thermal's got a lot of thumbs up in there in terms of how the behavior is performing.
Thank you. Our next question is from Daniel Reguera from Our Drone UI.
Thank you. My question is, there are a lot of people wondering here what programming languages were used for the onboard software, and how did you handle the computational redundancy? Thank you for your amazing work, and I hope you hear more about the James Webb Telescope. Thank you.
Processor languages? That's a good question.
I think it's C++. Okay, well, for our language, I believe it's C++. And I wasn't sure I caught the other part of your question, the redundancies?
Everything was redundant.
Everything, yeah, our computers were fully redundant, and I think that's about as much as I understood the question.
It's okay. Thank you for all. And what someone make the question, what next on the James Webb Telescope? And I'm wondering if you can extend any more the James Webb Telescope's life.
Well, when it comes to the James Webb Space Telescope life, right now, when we launched by design, our limiting resource was propellant. And right now, because of the efficiency or the accuracy with which Ariane put us on orbit, and our accuracy and effectiveness at implementing our mid-course corrections, we have quite a bit of fuel margin right now relative to 10 years. Roughly speaking, it's around 20 years of propellant. Roughly speaking, and that's TBD.
Thank you. Our next question is from Lee Roop from AL.com. Lee Roop, your line is open.
Yes, hello. Thanks for doing this, and thanks for taking my question. I'm talking to you from Huntsville, where we have been following this. People have been following this really closely since the launch, and I know that some folks down here built the sun shields and some other contributions. Is there anyone that could tell me, how did everything that we contributed to you guys, how did it all work out?
Yeah, there was a lot of contributions from Huntsville. I remember going down after we completed the first sun shield layers, so those big silver diamond shaped, patterns, 5 of them that give us this 600-degree Fahrenheit differential. right now look wonderful. We're already seeing something on the order of about 500 degrees in the differential between those layers. So with NextSolve down there, they did a wonderful job. The optics were also tested at Marshall Space Flight Center, 6 at a time, once with just bare beryllium to 150 nanometers of surface figure accuracy, and then again after being coated with their gold reflective layer for infrared down to better than 20 nanometers. And that's where laser interferometry techniques were perfected so greatly. They're used now for ophthalmology and LASIK. So in Huntsville, between Marshall and NextSolve in particular, tremendous contributions. I remember being down there for that layer one. I got a coin from the mayor of Huntsville there. I still got it on my shelf with all my other coins. So it was a proud moment for me and for the city.
Thank you. And that is all the time we have for the first question and answer session. We will now move on to the next set of speakers and hold another Q&A session later in the program.
Thank you so much. Thank you to all of our speakers. I will encourage you to step off and we will get our new group up here. Thank you so much and congratulations. And we have the next group coming in, filing in behind me. I'll let the noise go on behind me for a moment. As we mentioned, this will be a section where we start focusing on what's coming up next. For anybody for the last session who didn't get a question completely answered or has some more follow-up, as always, go ahead and write someone in the NASA Office of Communications and we will get you an answer or any more details. But for now, moving on to our second group. We have today John Durning, the Webb Deputy Project Manager at NASA Goddard, Lee Feinberg, the Webb Optical Telescope Element Manager at NASA Goddard, Jane Rigby, Webb Operations Project Scientist at NASA Goddard, and Heidi Hamill, the Vice President for Science at AURA, which manages the Space Telescope Science Institute. We're going to have the exact same plan as before. We'll have a couple of opening remarks from John Durning, and then we will switch right into the bulk of the time being for questions. As before, you would press *1 to get yourself into the queue for questions. So with that, passing on.
Hello, yes, my name is John Durning. Let's see, the last 2 weeks, 14 days, have been a spectacular success and set the table for the fantastic sciences to come. So on our panel we have 2 scientists to talk about that, but in the next 15 days we're going to get to our let's have a look. Okay. Then the next 15 days, or at 15 days from now, January 23rd, we will arrive at our L2 insertion location, and then we'll fire, as was talked about previously, our MCC2 burn and get into that. But while we're getting to that point, in the next 15 days, we will be phasing the mirror, taking those 18 mirror segments and aligning them so they essentially perform as one monolith. And Lee is on the panel here to talk about those. I'm sure there's questions about that. He's here to help you understand how that works. So without further ado, that's what's happening in the future. I should say also that we'll start turning on the instruments in the next week or so, and then after we get into L2, as the instruments get cold enough, they're going to start turning on all the various instruments so that we can cool down, do their own calibration activities to end the commissioning when they're all calibrated and ready for that first light. So with that, I'll turn over to the questions.
And once again, to ask a question, please press *1. And our next question is from Elizabeth Howell from space.com.
Hello, and congratulations again. This is probably for John. You just gave us a good roadmap of what to expect. Can you also give us a sense about which ones of these milestones, if any, would be the most technically complex, or the ones that could be potential difficulties, the ones that you're trying to manage the most, I suppose?
Let's see. So what the most difficult milestones ahead? Well, let's see. Each instrument has their own set of milestones that will be challenging to them once they reach temperature, making sure they get it all aligned. But there's nothing project or mission-wide that is a major milestone once we get an L2 and we start cooling down. the mirror themselves, I'll let Lee touch base on what are significant milestones over the next 10, 12 days as they align the telescope. So with that, Lee, you want to talk about what's coming up?
Okay. Yeah. So let's see. Starting on Tuesday, we'll start deploying the mirrors. So they're in a launch configuration, and there's about a 10 to 12 day process to get all of the mirrors forward by roughly half an inch. And that puts them in a position where we can do the detailed optical alignment. So this is sort of the first step. We call it mirror deployment. But then after that, there's actually a 3-month process to align the mirrors, starting with the very first light on all 18 segments. And at roughly 4 months into the mission, around day 120, is when we think the entire telescope will be aligned. But that's happening in parallel to the commissioning of instruments. So we'll be working closely with our instrument team partners, and they'll be turning on different instruments and turning on the cooler, and we'll then use those instruments to align the telescope and to further refine the telescope.
Thank you. Our next question is from Marina Corin from The Atlantic.
Hey, everyone. Congratulations. First one for Lee. Why did designers go with hexagon-shaped mirrors for this telescope, and how are you feeling about making those final segment adjustments in the coming days? And then a question for John. How many people in the mock have tested positive for COVID in the last 2 weeks, and how are you handling shifts and work moving forward as people have to go into isolation? Thank you.
Well, I guess I'll take the softball. So hexagons, actually there were a couple of different configurations very early on. It wasn't only hexagons, but hexagons are a really nice shape for making a mirror that you want to make in pieces. You know, if you think about the different geometries that you could use, like triangles and squares, those have very sharp corners, which we generally don't like when we make mirrors. We like mirrors that are symmetric. If you remember, there's an actuator at the center of the mirror that moves forward and back, and the hexagon shape works well with being able to change the curvature of the mirror. And we were able to put 3 mirrors on each wing, which really was nice to be able to fold it up. So that all worked pretty easily.
Okay, so for the COVID question, turns out we've overcome many challenges on this project, from hurricanes to earthquakes, you name it. So this was just another challenge that we faced, and we basically are following the CDC guidelines as far as distancing, wearing masks all the time, as you could see, as well as close contact, proximity. We have had positive tests here at the Institute, but fortunately we have testing. People, before they come on, have to be tested before they get into the facility, or show when they, you know, if they left their hotel that they've tested, and they test positive, they identify, they call the organization here at the Institute, the HR group, and they say they've been positive, and we have these trackers on us that, you know, proximity trackers that they can then take that piece of information and see who was in close contact to the people who had tested positive. And then we take the protocol that we need to do, which is isolate them and make sure that, you know, we don't have, they have to go and stay in isolation, take tests to make sure they're negative. So we've had that exercise a couple of times in the past 2 weeks. And we've actually worked out very well. There were very intense periods to do what we did the past 2 weeks of deployment, and we were able to accomplish that even with these positive tests, because we've been proactive, as well as we have workstations and our laptops that we can work remotely and still do the job we need to do. They're not as fancy as the workstations you see behind us, but they're sufficient. We can get the telemetry. All the engineers can work at their hotels, or if they're nearby at their homes, get their job done and be successful. And then we have taken the measure starting today, given, you know, the surge of COVID that's in the area, that we have decided to proactively reduce the in-present staffing in this room. We distribute it across the part of the building and remotely to homes, so that we even get greater distance than the CDC guidelines for the next couple of weeks as we work through the recent surge of the COVID around us. But we've been very successful accomplishing our task. Unfortunately, while there have been people with symptoms for COVID, most everybody has recovered from that exposure, and they seem to, if they're not back at work, they're trending in the right direction to come back to work. So it's actually a challenge we overcome, just like all the others we've faced. Thank you.
Thank you. Our next question is from Jeff Faust from Space News.
Good afternoon. A question for Lee. I wonder if you can go in a little bit more detail the optical alignment process. What steps are involved in getting all the mirrors aligned, and what sort of update can we expect along the way before you reach the final alignment in a few months' time? Thank you.
Yeah, I'll go through the alignment and then I'll pass it to Jane to go give you how we'll be updating. But basically, you know, the first thing, it's kind of a unique thing here because we have this 18 segments, and we expect them to be very misaligned. You know, we just literally deployed a wing, so this is not a perfect monolithic mirror at this point. So when we take what we call the first light of the telescope, we're actually expecting to see 18 separate spots that are probably going to be pretty blurry because everything's going to be misaligned. But it's essentially like we're going to have 18 separate telescopes. And the first thing we're going to have to do is sort of align those individual telescopes, those individual primary mirror segments, and then we're going to take all those 18 spots and put them on top of each other. We call that stacking. But at that point, we still don't have a nice tight, you know, a star doesn't quite look like a star. It's still going to be very blurry. And we have to go through the process of aligning the mirrors to the point at which they're actually aligned to a fraction of a wavelength of light. And we use a series of algorithms that we developed actually very early in the program to demonstrate this program is feasible. We demonstrated them on a scaled test bed. And we have models that simulate all this, but this will be the first time that we do it on the flight telescope with real stars. So we're real excited. It's a little bit of a long process, but at the end of it, we expect to see an image of a star that looks like a star. And then we expect to get that over the full field, which means all 4 instruments will have beautiful images. And I'm going to pass it to Jane to talk a little bit about how we'll be communicating some of this information to you.
And I should just add that to add a little bit to what Lee said, you know, just the change of alignment. We start with the mirrors off by millimeters, and we're driving them to be aligned to within less than the size of a coronavirus, right? Like to tens of nanometers. It's this very deliberate process that is time consuming. So yeah, like just so everybody knows, the first images that we take are not, this telescope is not ready out of the box. The first images are going to be ugly. It's going to be blurry, and as Lee said, 18 of these little images all over the sky. So we have to drive that into one telescope. I like to think of it as, it's like we have 18 mirrors that are right now little prima donnas all doing their own thing, singing their own tune in whatever key they're in, and we have to make them work like a chorus. And that is a methodical, laborious process. We want to make sure that the first images that the world sees, that humanity sees from this telescope, do justice to this $10 billion telescope and are not those, you know, hey, look, a star. So we are planning a series of WOW images to be released at the end of commissioning when we start normal science operations that are designed to showcase what this telescope can do, and that showcase all 4 science instruments and to really knock everybody's socks off.
Thank you. Our next question is from Alexandra with Nature Magazine.
Hi, thanks. I have a follow-up on that, I think for Jane as well. I'm really curious about like where the photons are coming from during this whole commissioning process. What are sort of the astronomical targets you'll be pointing at during alignment and commissioning, and where are those photons coming from that will be bouncing around in the scope for the next couple of months?
So the first images, the first targets are some stars that are the brightness that Lee and team need. So they're not, you know, they're fainter than your eye can see, but not by a whole lot. They're reasonably bright stars. So for the first part of telescope alignment, that's it. We look at some stars. That's kind of boring. Then as we get into, but important, as we get into science instrument commissioning, which is the last 6 weeks of this 6-month process, then we start looking at a larger variety of targets. That's where we're checking that all 4 science instruments are working correctly. Those targets are chosen not because they're scientifically amazing, but because they're useful. Things like wavelength calibration, things like we have some sources that are nice and uniform brightness, so we can check how the detectors are working. So there's a bunch of calibration and checkout that's happening. A lot of those targets are in the Large Magellanic Cloud, because we can always see the north and south ecliptic poles. They're always available. So looking out of the plane of the solar system up and out of the plane of the solar system down, that's always available. So a lot of our targets for commissioning are there because then we didn't have to keep replanning if the launch date changed.
Thank you. Our next question is from Jim Siegel, NASA Tech.
Thank you. Obviously, the number of scientific, engineering, and even educational achievements will be very significant from James Webb. However, I'd like to ask you if you could, if the ordinary people, so to speak, on Earth, the rest of us Earthlings, what can I tell my readers of those people about what this James Webb telescope means to them? Thank you.
Hi, this is Heidi Hamill. You know, what you can tell ordinary people about this telescope is that it's an example of what NASA and its collaborators can do when they work together. When NASA and ESA and the Canadian Space Agency work together, they can achieve remarkable things. You've heard people talking about how, oh, it looks so easy. It is not easy. NASA makes it look easy, and sometimes they're a victim of their own success because it looks easy, but it's not easy. It's very challenging. And I think that we all, as humanity, can be proud that we are working collectively to do great things, to expand our knowledge of the universe, to make the universe more accessible to all of us. All of the pictures and all of the data and the knowledge from this telescope will be shared with all of the taxpayers who paid for it. So this becomes a part of our legacy to the future, this exploration that we as a team have been doing. So I think that's something you can share with the ordinary person.
Thank you. Our next question is from Irene Klotz, Aviation Week.
Thank you.
Actually, can I just add a little bit to that?
Can you hear me? Have you actually selected a target, boring or otherwise, that's going to be used for the mirror alignment and the image stacking? And if so, could you please provide the name or the designation of that target? Thanks.
There's a list of stars that are bright enough, and we'll look up which ones are observable now, and we'll pick one of them. But just to go back to a minute to the previous question, I just wanted to add a little bit and say that I think if you look at a really big picture of what is the science that we're doing with this telescope, it's understanding what is our place, where do we all come from, and like how do we fit in to the universe? How did we get here? How weird are planets like the Earth? How did our galaxy and our solar system come to be? And so, you know, for an average person, that's also a very personal question. How did I get here? What is my history? Not just of my own life or my own ancestors, but how did we all get here? How did it all happen? That's the big, big, big picture that we're working on.
Question comes from Reese Nations, The Well News, Washington, D.C.
Hi, thank you. So large parts of my question were pretty much already touched on, but I was wondering, you know, given the launch accuracy and the accuracy of the mid-course corrections on the way to L2, is there any possibility that we might be able to see the first clear images from the James Webb a little bit early ahead of schedule sometime in June?
Yeah, I mean, so one of the things that we're paying very close attention to is how the telescope and the instruments are cooling, because actually what prevents us from getting images even sooner is how long they take to cool. It turns out actually early in the mission we did find things were cooling a little bit faster than our models had predicted, and so it does look like there's a potential maybe of a day or two faster, but not significantly faster. So basically our original timeline is close. We might be a couple days before that.
Thank you. Our next question is from Felipe Orgolski from Polish Public TV.
Hello, I hope you can hear me. My name is Filip Ogorzelski from the Science Channel of the Polish Public Television. First of all, I would like to thank you for the opportunity to see the launch of the James Webb Space Telescope live in French Guiana. Now we are preparing a documentary movie about the JWST mission called A New Window to the Universe. So, now we know that the most of the dangerous and difficult steps are behind us. And I'm very happy about it. So, do we have any future steps of deployment and calibration to be concerned about, or can we be 100% sure that the JWST deployment is a complete success? And maybe, what are you the most proud of when it goes to the whole mission?
I'm sorry, I didn't catch the 100% sure of what? Excuse me, can you repeat the 100% sure of what? I didn't catch that.
Can we be 100% sure that the JWST deployment is a complete success?
Oh yes, we can confirm that the deployments that just have taken place has been 100% successful. We have the telemetry and the performance that matches our predictions. So we know for sure that the telescope is deployed the way we wanted it to be deployed. Oh, what were we most proud of? Oh my gosh, we were most proud of the collaborative effort to reach this moment. I mean, for me, it's been 15 years. For Lee, it's been longer. And for Jane and for Heidi, it's been equally. Many years put in of sweat and labor to get to this point. We're most proud of looking at that screen that shows an image of what's on an orbit, but knowing, based on telemetry, that that's what it looks like. It is a fully deployed telescope ready to perform fantastic science to expand our knowledge. So that's what we're all, me personally, that's what I'm all very proud of. If you want to add anything?
Well, I just want to say one thing is, from an optical perspective, we still have a long way to go. So this was an incredible achievement, one of the most amazing, achievements in space that I've personally ever witnessed. But we're not there yet. We still have to deploy all the mirrors. We have to align all the mirrors. We have to get all the instruments working. And so I will tell you, the engineering team is not resting. We're still, we still have that drive, and we have a few long months in front of us. I think when we have, images that look like, fine images, that's when we're really going to be 100% confident in everything. So that's kind of, I just wanted to share that.
And I'm going to add that I'm just a scientist. I wasn't involved in building this telescope, although I've been involved in the advisory process for over 20 years. But what I'm really proud of is the fact that this engineering team that we are celebrating today has done such a fantastic job of getting us from just concepts 30 years ago and then just drawings and then pieces to a fully deployed telescope that Lee and his team is now going to focus, and eventually the scientists will get to use. I think we're all proud to be a part of that team and proud of the achievements of the engineers today to get us to this point.
We're at about 3:30, but we have quite a few questions left, so we are going to extend and keep answering questions. So have at it. Thank you so much.
Thank you. Our next question is from Marcia Dunn from Associated Press. Marcia, we're not able to hear you. I think we'll move on to the next question. Our next question is from Stephen Clark from Spaceflight Now.
Thank you, and congrats again. A couple of quick questions, hopefully. First of all, can someone just confirm on the record that NASA is not planning to release any of the early images, those blurry, fuzzy images of Starlight? I just want to confirm whether those will be released publicly as they are gathered, or will we not see any images until that big public release in the summertime? And also, is there a chance that the L2 insertion burn, I think on the 23rd of January, based on what you're seeing with the trajectory, is there a chance that that could be deleted or deferred? And that would afford you some further fuel savings. Just wondering about that. Thanks.
I'll answer the second one. I know the confirmation. Yeah, okay. To your first question, the plan is still to issue the releases at one time, not on the way. But the other answer is the burn is targeted for the 23rd. It has to happen, but it is a low-risk burn, and we have tolerance. If we miss it by a day or so, for whatever reason, we're fine. But yes, so the burn is targeted for the 23rd, but there is some flexibility around it. Okay.
So I think one of the watchwords for all of commissioning is flexibility. Things are not going to go exactly the way we expected, and that's okay. We have a timeline for commissioning that is this Excel spreadsheet that has down to the minute how we're all going to be spending the next 6 months of our lives. And we all know that that is not actually the timeline we're going to execute, but that's the plan, and we will move it around as we need be. The current plan is, yes, that we're going to hold the images to release at 6 months when all 4 instruments are ready for science. But we have to be flexible during this process, and so I'm going to leave it at that.
Thank you. Our next question comes from Manuel Mazzanti from Debate.
Hello, everybody. Congratulations on this incredible day. I'm still curious about the speed of the telescope. We know that it's slowing down day by day. We went from several kilometers per hour to 0.4 kilometers per hour right now, per second. And I was wondering, what is the speed that you are planning the telescope to have when it reaches the L2 point? And it has to be a precise speed in order to exactly do the L2 burn. Thank you.
So, I don't know this precise speed, but it is driven by physics. So we have our trajectory, and it's going to slow down by just the orbitodynamic phenomena at the trajectory we're at. And we already can calculate what that is. I don't know firsthand, but we have our burn maneuver factoring in the speed we're going to get when we get there. So it's really pretty much basic physics at this point, how it'll slow down and get to its L2 junction.
Thanks.
Thank you. Our next question is from Leo Enright from Irish Television.
Thanks again. Today would have been Stephen Hawking's 80th birthday. Now, Stephen absolutely loves coincidences, so I'm quite certain he would have been chuffed by this coincidence. The question is almost impossible, I think, which is why it must be for Heidi. Can you talk, is there anything you can say about what JWST will be doing that might give us further information about the stuff that Stephen Hawking cared about so much, thermodynamics of black holes, Hawking radiation, Penrose stuff, all of that good stuff?
I'm going to take that one because I love black holes. Right, so the Webb Science Program for the first year, we are going to be doing more than 300 different science programs that were submitted by researchers from all over the globe. It was a cutthroat competition. We rejected 3/4 of all the accepted proposals. And we're taking the top-ranked quarter. Those include quite a few proposals to study black holes. Most of those are to study black holes that are in the centers of galaxies. It turns out that every galaxy has a black hole lurking in its center. Big galaxies have big black holes, little galaxies have little black holes. We don't know why. But when I tell this to school kids, they're like, that's fair, it's sharing. But we don't actually understand how that evolves to be. One of the projects I'm really interested in is a project to look at the first the most distant quasars that have ever been found. These are billion with a B solar mass black holes that we see as they looked only a couple 100 million years after the Big Bang, so very far away. That light's been traveling through time for almost the whole history of the universe. And nobody really knows, how do you make a quasar? How do you put a billion, suns worth of stuff in a black hole and get all that done in only a couple 100 million years? Nobody really knows, but we found them, and that's going to be one target to go study those. And then there are other programs to see how those black holes and their galaxies have co-evolved through the history of the universe.
And I'm just going to jump in here to make a pitch to remind people that the core science of this telescope was to see the very first light in the universe, the first galaxies that formed, with some clever projects, perhaps even the first stars that formed. And that's its raison d'etre. That's why it was built the way it was built. But this is a great observatory that not only can do that science, but also the black hole science that Jane was talking about. Also, the cosmic evolution of galaxies over time. Also, probing the atmospheres of planets around other stars, looking for the first stars that are forming inside dusty nebulae in our own Milky Way galaxy, and even exploring many things in our solar system, which is my field of science, which is why Jane took that question. But we will have a really robust program of solar system observations to complement the in situ spacecraft work that we're doing with the NASA Planetary Science Division. And this is the power of Webb, just like it has been the power of Hubble. With a great observatory, you can do amazing science over a vast range of astrophysical topics. And that is why we as a community have been so excited about this day, getting to the point where this telescope is on its way to get our science done, starting about 6 months from now. Thank you.
Thank you. Our next question is from Don Ladia from BBC.
Thank you for taking my question, and congratulations. My first question is for John or Lee. Are you able to provide an approximate date for when instruments like the Fine Guidance Sensor or NIRIS will be tested and calibrated? And my second question is for Heidi. Are there any plans to use Hubble to take an image of its successor, JWST, at L2? Thank you.
Yeah, so the fine guidance sensor, the key there is getting the detectors cold enough. The first instrument that'll come on is the near infrared camera, which takes the images, and that comes on in between days 30 through day 40. The NIRCam instrument will come on the fine guidance sensor will come on about 10 days after that. We have to get the detectors cold enough. And then as soon as it comes on, we'll start using it while we're doing the alignment process. And in fact, looking at a star to guide early on, and then we'll eventually transition to using stars that come from all 18 mirrors. So there's a whole sequence we do, and we want to get that guider on as fast as we can, but we have to wait for the detectors to get to temperature.
The question of whether Hubble will be used to look at Webb is a question that has been asked a lot in social media. And also in social media, there are many, many images from even amateur astronomers who have been tracking James Webb Space Telescope, already imaging it. The challenge here is that James Webb Space Telescope is so far away that even for the power of the Hubble Space Telescope, we cannot resolve it to more than a point source. And so we could see a point source and see it moving, but that would not be scientifically useful for us. What if you would say, well, maybe you can see the brightness variations? We can do that with ground-based telescopes. And so we don't need to use the Hubble Space Telescope to do those observations of the James Webb Space Telescope. And we have many, many other astrophysical things that we want to use Hubble for. And so I think it is unlikely that we will use Hubble to look at Webb because there's no scientific or engineering reason for it. But, Jane points out, what we as scientists are really excited about is using both Hubble and Webb together to study the universe simultaneously. And that's because we care about the colors of the light from objects in outer space. And the Hubble Space Telescope is focused primarily on ultraviolet and visible light and a little bit of near-infrared light. And then Webb picks up at the near-infrared and pushes out into the mid-infrared. So you get a much broader wavelength coverage of your astrophysical objects by using both of these telescopes together. And that's why we're very excited that both are going to be operational at the same time.
Thank you.
Thank you. Our next question is from Ken Kramer from Space Up Close.
Hi, thank you for doing this, and congratulations again. My question is for Jane and Heidi. I wonder if you could talk a little bit about using the telescope to look for life beyond Earth in our solar system. Dr. Sabuchan talked about this a lot even this morning at targeting Europa. So I'm wondering when that might happen, and which instruments will you use, if we could talk specifically about that, what you hope to learn if there's an emission there, and will you look at talk about other targets you might look at in our solar system for that, Enceladus, maybe Triton. Thank you.
One of the programs that we plan to do with some of our guaranteed time is to target the areas in the southern part of Europa's, Jupiter's moon Europa, and Saturn's moon Enceladus. We have evidence from the Hubble Space Telescope that there is water jets emitting water from possibly from the subsurface ocean of Europa. That's Hubble observations. For Enceladus, the Cassini spacecraft actually got images of jets of water erupting from the southern pole of Enceladus. It flew through that and sampled it and determined that it was water. What we will try to do with this time is image the plume area, and more so than images, that's not the important part. The important part is we're going to try to do spectroscopy. That means taking the light from that region of the southern poles of those tiny moons and spreading it out into a rainbow of colors, and then looking at that rainbow of light for the chemical fingerprints of molecules in that water. We'll be looking to see if there is carbon dioxide. Is there methane? Is there formaldehyde? Those carbon-bearing products could be evidence of activity in the subsurface, the sub-ice oceans on those worlds. We're very interested in those worlds. And so what Webb can do is it can provide additional information about those plumes and what material could be dredged up from those sub-ice oceans into this plume material. I will say it's a risky observation. Risky in this way, not risky to the telescope, but risky in the sense that we may not see anything. Those plumes are not always active, at least on the case of Europa, it seems. And we may make an observation and see nothing. And that's tough. That's why we're using the guaranteed time that I have. A proposal to do this, like Jane was explaining, you're not going to get a proposal approved for something that may not give you any science. So that's why we're using this guaranteed time to do that. Triton, we'll be looking at Triton, but it's too far away, I think, to really do this kind of chemistry. We will be looking at surface chemistry of Triton, just as we are looking at surface chemistry of all the Kuiper Belt objects, Pluto, It's Moon Sharon, Eris, Makemake, any Kuiper Belt object that has a name, we're likely going to be looking at it with Webb. We will also be looking at Saturn's moon Titan. Titan has a thick atmosphere, what we call a prebiotic atmosphere. And we will be able to look at atmospheric clouds with the infrared power of Webb. We can look through some of these clouds to the surface, perhaps even detect the evidence for lakes on that moon. We know there are lakes there from the Cassini mission. So that's another very interesting, what we call astrobiological target because of the interesting prebiotic chemistry in that atmosphere. Did you want to talk about exoplanets? Sure. Yeah.
So Heidi just talked about our own solar system. We now know that solar systems are really common in our galaxy, that on average there's a planet for every star, which still blows my mind. And so about a quarter of all the time in the first year of Webb science operations will be spent studying planets orbiting other stars, exoplanets. And so those observations include studying planets that are nothing like the Earth, right, that are massive, Jupiter, Saturn, or Neptune-like objects. They also include planets that are more like the Earth, that could be rocky. In particular for Webb, Webb can study planets that are in the habitable zone, that is, that might have liquid water. They're at the right temperature distance from their sun to have liquid water. Webb can do that for solar systems that aren't like ours. Webb can do that for planets orbiting red dwarfs. So there are programs to do that. That's where we'll have our best shot at looking at rocky planets. And so I think Webb's role in that is, it's part of the story. Webb's role is to look at those types of systems of rocky planets orbiting red dwarfs and tell us whether whether the atmospheres of those planets have water vapor, whether they look temperate, whether they look, moderate temperatures. It is not the life-finding machine. That would be another future telescope.
Thank you. Our next question is from Marcia Smith from spacepolicyonline.com.
Thanks so much. I think my question is probably to both Jane and Heidi. And could you clarify whether it's Aura or NASA that oversees the selection process for who wins to get observing time? Or does one of you do it for the guaranteed observers and the other does it for the guest observers? Just how does that process work? And as part of that, if someone proposes something to use both Webb and Hubble, does that get priority because Hubble is so old and we don't know how long it's going to last? And are any of the 300 that you're going to do in the first year using both Webb and Hubble?
So let me talk a little bit about the process of deciding who got time on this telescope. The people who were serving on the science working group and building instruments had some guaranteed time. I'm one of those people. And that time we get to choose ourselves. What we are going to do has to be feasible, of course. Once that was set in stone, then there was a call for proposals that went out to the world. Everybody can apply for time. This is a process that's overseen here at the Space Telescope Science Institute, which is managed by Aura. But Space Telescope here, the people here, form review panels, and they assess every one of those proposals. They read them. They don't know who wrote them. These proposals are evaluated in a dual anonymous way so that all you can see is the science, and they rank them. And the really great ones get the time. The ones that needed some more work or didn't even need Webb, they don't get time, and they debate the ones in the middle, and they fill up the time accordingly. So it's a very rigorous process. As Jane explained, many people propose, but they don't get the time. Every year there'll be another call, and so you'll get another shot, and the year after that, and the year after that. In terms of Hubble and Webb together, I actually want to flip the question a little bit, Marcia. I will share with you that there have been programs being done with Hubble in preparation for James Webb Space Telescope. really focusing, for example, on Hubble's UV capability, so that all of those observations are in place, so that when Webb does the observations, there's complementary Hubble observations as well. Do you know about Hubble Webb together? Okay, I'm going to let Jane answer the next part.
Sure. So, and just to go back to you asked about the formal relationship. So formally, NASA delegates the authority to the head of STSCI, the Space Telescope Science Institute. So the authority to select the Cycle 1 General Observer programs is delegated to the head of Space Telescope Science Institute, which is overseen by Aura. And then NASA has oversight over that process. So I got to be an observer watching that whole process happening, sitting in on a lot of those meetings. As far as doing joint time, it is a common thing that we do with more established missions to do joint time so that observers can apply, one proposal to get time on two NASA facilities. We didn't do that for the first cycle of Webb because we figured it would be really, really oversubscribed. There'd be many proposals. We got over 1,000, and we just wanted to keep things a little simple. That is something we are exploring for the second year. Of doing some joint proposals with Webb and other missions like Hubble.
Thank you. Our next question is from Daniel Ruggiero from R-Drone UI.
Thank you. Thank you all for this time. I have 2 or 3 questions. One of them is the amateur people want to know, this is a really easy question, what's the focal distance of the James Webb Telescope? But my question on this is, will you really study on our opposite position of the galaxy, not to the center of the galaxy, that the place that people names beyond south wall of the galaxy? And the other one, the last one, excuse me, is regarding interstellar objects like Oumuamua. If the director of science have a discretional time for redirect the telescope in case we have in advance information of one interstellar object coming to our system. Thank you. Thank you for your time and your wonderful work.
Focal length is easy. So the effective focal length is about 134 meters. So not to be confused with back focal distance. It's just, there you go.
I can answer the third one about an interstellar object like Oumuamua or Borisov. We actually have what we call a target of opportunity proposal already approved and in the queue. And therefore, if we do find an interstellar object, we are ready to do the science observations for that.
And to follow up on that, there is discretionary time that the director can choose, generally for things that could not have been foreseen at the time of our annual call for proposals, which tends to be stuff blowing up, stuff going boom, or stuff zipping through our solar system from elsewhere in the galaxy. So there is an opportunity for those sorts of unprecedented, although in this case it was precedented and they planned it and it's a proposal, but for things that are truly like, oh my gosh, no one could have foreseen this, there is an avenue for those ideas to get in really fast into the system and get those observations out in a very timely manner.
Our final question today is from Irene Klotz from Aviation Week.
Thank you. Just real quick, I wanted to clarify the date of the MCC-2 burn. The NASA Explorer tool shows it on L+26, not L+29. Was that changed or was that incorrect? So it is scheduled for the 23rd and not the 20th?
Correct. It's scheduled for the 23rd. L+29 is the plan.
Thank you.
Thank you all so much. These were really great questions and wonderful answers. I really enjoyed listening to them. We are going to finish up this telecon. As always, you can send us more questions or get details hammered out if you need to by sending an email to the Office of Communications. You can travel along with us through the rest of the journey at nasa.gov/web or web.nasa.gov. Both work. Lots of information at both places. And thank you so much for being here.
I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon.